Hello guys and welcome back to another class of our course about the complete introduction to quantum computing. So in today's class we are going to talk about the first type of algorithms. So basically in this part of the course we're going to talk about different algorithms that are used in quantum computing, and we are going to start with the Fourier transform algorithms. So basically what I'm going to do is I'm going to present a few algorithms. I'm not gonna make all the mathematical explanation for each algorithm and talk about all the maths behind it. And once again, my goal here is really just to give you an introduction to the subject as well as an introduction to the algorithms. So let's start. All right. So for the Fourier transform algorithms, well, basically the quantum Fourier transform algorithm can also be seen as a linear transformation on a qubit. So basically linear transformation that will work with qubits. So in other words, it can also be seen as the quantum version of the inverse discrete Fourier transform. And this type of quantum algorithms is part of plenty of different algorithms, such as, for example, we can see here the Simon's algorithm or the Shor algorithm, that is one of the most popular. So basically, it can be performed really efficiently. Well, it can be performed efficiently on a quantum computer. So basically, the Fourier transform algorithm is really made for quantum computing, and well, it's as I said here, it's the quantum version of the inverse discrete Fourier transform. But basically, this type of algorithm is really made for quantum computing and can work perfectly when used on a quantum computer. So for the two algorithms that we are going to talk about today, we are going first of all to talk about the Shor algorithm. So basically, what exactly it is. So what we can say about this algorithm, first of all, so for the Shor algorithm, is that it's a polynomial time, or in other words, a time complexity algorithm for the composition of a composite number into a product of smaller integers, or in other words, integer factorization. Sorry. So it can, for example, define the prime factor of certain integers n. So let's say we have an integer n, and what I will do, it can define the prime factor of this number, so of the number n. So this is for the Shor algorithm. For the Simon's algorithm, it's a bit different. So first of all, it has been created by Daniel Simons in 1994. And basically, this algorithm has been extremely useful to solve some kind of problems, and has been created especially to solve the Simon's problem that have been created with by Simons as well. So what exactly is the Simon's problem? So basically, the Simon's problem is simply a computational problem that can be solved way faster with a quantum computer that with a traditional computer. So basically, this problem is not necessarily, well, let's say something that is complex or really useful in real life, but just a certain problem that can prove that quantum computing works way better. Well, quantum computing is way faster than traditional computing. And basically, with the use of the Simon's algorithm, it's possible to solve this problem way faster with this algorithm than to use a traditional computer, for example, as well. So for both of those algorithms, the use of it can be in, for example, quantum research. There are places where you can use those algorithms, but it's not it can be used in real life, but it's usually used in places, for example, in research. It can be used, for example, I don't know, in physics. It could be used in mathematics, in engineering, in electricity. So in fields that are really scientific and that requires a lot of mathematics, it's really used a lot in quantum research, especially the Quartz algorithm, which is really, really popular in this field. And basically, this is, for now, this is the main goal of them. So they're really used in research to be able to build the future quantum computers. So I hope right now you understand a little bit more the first, well, some of the algorithms of, well, in quantum computing that we have. So that's it for this class, guys, and see you all in our next class.